exploring an interesting work from Netflix, Go with the Flow, a paper that turns random noise into something extraordinary. Imagine controlling the motion of objects, guiding a camera, or even transferring movement from one video to another, all powered by warped noise. So, what's warped noise? While Gaussian noise is pure randomness, warped noise introduces structure by aligning with the motion in videos through optical flow. Think of it as giving noise a GPS to follow, so that the noise evolves over time in a way that aligns with the motion in the video. This method beautifully harmonizes chaotic noise with optical flow, delivering precise motion control without compromising quality. And here's the really cool part. It's fast enough to run in real time.
Let's dive right into the main idea behind controlling motion in video diffusion models. The method we're exploring focuses on structured noise rather than complicated model changes. Imagine taking random noise, like static on a TV screen, and reorganizing it to align with desired movements. That's basically what happens here. Instead of sampling random temporal noise, we use warped noise guided by optical flow, while keeping the noise random in the spatial dimensions. Look at Figure 1. Do you see how it shows multiple ways to manipulate motion? First, there's local object control, where you can animate just a part of an object without affecting anything else. This is handy if you want, for example, only a character's arm to move, while the rest of the character stays still. Then we have global camera control, which uses depth maps to create natural panning or zooming effects. Finally, motion transfer lets you take the motion from one video, like a flowing river, and apply it to a completely different scenario. All of this runs in real time, without modifying the original diffusion model architecture. During training, motion controllability becomes an inherent feature, opening the door to all sorts of creative uses, from special effects to more practical editing tasks. Now let's talk about why generative modeling is all about turning chaos into something meaningful. Typically, these models start with random Gaussian noise and gradually refine it into an image or video. But how do we handle motion control? Traditional solutions can be too rigid or require heavy modifications to the underlying model. Sometimes they don't generalize well, or they sacrifice visual quality. The trick here is to work directly with the noise. Think about random noise again. Normally, it just evolves chaotically. But what if we inject motion data from optical flow, so the noise knows how things should move between frames? That's the core idea. Warp the noise with real motion cues and let the model do the rest. It's done at the noise level, so we don't have to change the diffusion model's architecture. Check out how this new noise warping algorithm can run quickly, even in real time. It warps noise frame by frame, ensuring smooth motion without the complexity of previous lengthy methods. This efficiency makes it scalable for large training sets and also really flexible, whether you're animating objects or transferring motion from a reference video. And it still maintains temporal coherence and high-quality visuals, thanks to how neatly it fits into standard diffusion pipelines. Let's look under the hood of how everything is pieced together. Three main components are at play: extracting motion via flow fields, warping the noise in real time, and fine-tuning the diffusion model. Together, they convert random noise into something structured and motion-aware. That's how we can get smooth, realistic videos. If you peek at Figure 2, you'll see how it all comes together. Optical flow, or depth data, is first extracted to capture how pixels move. Then, that motion information dictates how the noise evolves over time. Finally, the diffusion model gets fine-tuned so that outputs match the motion prompts or initial frames. The authors highlight three big contributions. 1. A simple yet powerful way to add motion control to all sorts of diffusion models without redesigning them. 2. A noise warping algorithm that balances spatial consistency and smooth motion with minimal computational cost. And 3. Evidence from experiments and user studies that it improves quality, control, and user satisfaction for tasks like local object animation, motion transfer, and global camera movement. It also addresses the long-standing challenge of ensuring temporal consistency in video generation by focusing on how noise changes from frame to frame. Ever wonder what kinds of motion you can control? There are generally three scenarios. First, there's object-level control, where you guide an object's position over time, like bounding boxes or masks telling the model where and how to move a particular subject. Second, there's global camera movement, where you control the entire scene's motion for effects such as panning and zooming using camera pose data. Third, there's motion transfer, where you take the movement from one video and apply it to another, preserving scene integrity in the process. Here, the noise warping method, called Go with the Flow, takes center stage. It pre-processes the noise itself before feeding it into the diffusion model. That means the model receives structured noise already embedded with motion cues, no extra complexity needed. Algorithm 1, shown in the paper, outlines how noise in one frame transforms into noise for the next. Instead of a slow rasterization step, this algorithm uses the optical flow to warp noise at each frame rapidly. It dynamically adjusts pixel density, spreading it out when needed, expansion, or tightening it, contraction. That makes it both fast and good at preserving detail, so it works well even in real-time applications. Let's dig deeper into how this warping handles expansion and contraction of noise while maintaining its crucial Gaussian properties. Picture a grid of noise pixels in one frame. In the next frame, some pixels might move apart, expansion, while others merge, contraction. Optical flow guides these shifts so that each region's noise density remains consistent with the underlying motion. Look at Figure 3 to see a visual breakdown of these processes. You'll notice how the algorithm balances expansion and contraction so that the final noise distribution still looks random, which diffusion models need, but also follows the motion we want. Two important mathematical results back this approach. One shows that the warped noise keeps its Gaussian distribution, so it won't throw off the diffusion process. The other proves it runs in linear time, which matters a lot if you're dealing with huge datasets or many training iterations. The paper also points out that this warping can plug seamlessly into workflows for both training-free methods, like super resolution or relighting, and fine-tuning scenarios where we want the model to explicitly learn these motion patterns. It's pretty adaptable. Now let's discuss noise degradation and how it gives you finer control over motion. By adjusting the degradation level, you decide how strictly the final video should follow your input motion. Higher degradation means more randomness is introduced, so the motion is smoother but less rigid. Lower degradation locks the video more tightly to the input flow, giving you very precise motion control. Check out Figure 4 if you want to see examples where the video sticks closer and closer to the specified motion as degradation goes down. During inference, the warped noise, derived from your video or motion data, acts as the starting point for the diffusion process. Interestingly, the method relies on deterministic samplers like DIM and doesn't need the diffusion model's architecture to be altered. This flexibility shows up when you're moving objects with a simple polygon-based interface. Just draw shapes and specify how they should move, rotate, or scale. The algorithm then creates synthetic flows that guide noise warping, and the diffusion model produces the video. You can do motion transfer or camera control the same way. Their only difference is where you get your optical flow. From a driving video, if you're transferring motion, or from user-defined transforms, if you're simulating camera moves. Once again, the degradation level plays a role in how faithfully you follow the driving video's motion. For implementation, they trained on a large dataset of around 4 million videos, using powerful GPUs to handle the heavy lifting, ensuring the final approach is robust and scalable. Let's switch gears to experiments that measure 3 things: how well the noise stays Gaussian, how fast the algorithm runs, and how good the video editing results look. For Gaussianity, the authors used metrics like Moran's I and the KS test, and the warped noise came out almost indistinguishable from perfect Gaussian noise. Interpolation-based methods like bilinear or bicubic warping, by contrast, fell short on preserving the noise distribution. On the efficiency side, take a look at the performance numbers. The proposed method is significantly faster than baseline approaches, up to 26 times faster in some comparisons, because it only needs linear time. That makes real-time processing feasible, even on big diffusion models. Finally, for video editing tasks like super resolution or portrait relighting, the paper tests the noise warping on top of pre-trained models like DeepFloyd IF and Diff Relight. The warped noise ensures temporal consistency across frames. Metrics such as PSNR, SIM, and LPIPS gauge the frame-by-frame quality, while a separate warping error checks how smooth the motion is over time. Compared to methods like InFres or HIWYN, this approach shows stronger temporal stability, especially around tricky areas like moving edges or backgrounds. Check out Table 1 for a more detailed comparison across multiple benchmarks. You'll see that the proposed method consistently leads in Gaussianity, speed, and overall quality. Some methods might do 1 or 2 things well, but here you get a good balance of efficiency and temporal consistency. The paper then talks about video relighting for complex camera motions. The authors tried challenging setups like a 180-degree camera sweep or a zigzag path. The approach handles subtle details, like beards or skin reflections, quite effectively. It keeps image quality and temporal metrics high, showcasing the model's adaptability. Local object motion control adds a user-friendly interface to define motion via polygons and cut-and-drag trajectories. If you look at Figure 5, you'll notice objects being moved along specific paths while the rest of the frame remains stable. Evaluations against other methods, like SGI2V or drag anything, indicate stronger motion fidelity and fewer artifacts. This highlights how the warping can precisely match user-defined motion, even when multiple objects are moving independently. So how does this method stack up for broader motion control and transfer? Qualitative tests show that competing methods, for example SGI2V or drag anything, might misinterpret local edits, producing awkward or unnatural changes in other parts of the video. The proposed approach keeps the object's appearance and 3D consistency better, even when handling complex things like water splashes. Look at Figure 6. You'll see examples like a squirrel and a puppy being viewed from different angles, mimicking camera movements. Compared to motion clone, these outputs stay sharper and more precise. There was also a user study with 40 participants, and a big portion of them, 82% for local motion control and 90% for camera movement, preferred the proposed method's results over alternatives. Motion transfer and camera movement get similar praise. Optical flows borrowed from reference videos help replicate detailed motions accurately. The paper mentions datasets such as Davis, DL3DV, and Wonder Journey to cover a range of scenarios. According to metrics like FID, MIOU, and FVD, the proposed solution maintains better pixel quality, motion accuracy, and smoothness over time. It outperforms other motion-focused methods like diffusion motion transfer and motion clone on these benchmarks. Let's now explore 3 key tasks where this approach really shines: motion transfer, camera movement control, and first frame editing. For motion transfer on the Davis dataset, you can see in Figure 7 how it delivers smooth, realistic motion for scenes like snowboarding or hot air balloons. This contrasts with baselines that can produce choppy or mismatched movement. When it comes to camera movement, look at Figures 8 and 9 on datasets like DL3DV or Wonder Journey. The method uses depth data to simulate natural 3D camera moves, and it manages to keep the visual details coherent throughout. Some other approaches might end up with random pixelations or jerky transitions. The first frame editing trick is also neat. If you edit the first frame, like adding an object, the algorithm carries that edit over every subsequent frame, preserving the original motion. Figure 10 shows examples compared to motion clone and NEV2V. You'll see that the proposed method integrates the newly inserted elements more naturally. Quantitative results, like FID and FVD, back up these observations, proving it keeps the video looking good and moving correctly. Finally, let's take a look at the ablation studies. Ever wonder what happens if we remove the motion conditioning or do lower rank fine-tuning? The performance drops. Specifically, if you rely on just text prompts without the warped noise, you lose a lot of the motion fidelity and video reconstruction detail. Metrics like FID and code tracker MIOU confirm this drop. Higher rank fine-tuning methods seem crucial too. LoRa with a lower rank doesn't capture the warped noise distributions as effectively, leading to poorer results. And if you remove noise degradation, you get tighter motion control, but might lose consistency in objects. Wrapping up, the paper introduces a noise warping algorithm that seamlessly adds motion control to video diffusion models. It turns random noise into motion-aware noise without needing big architectural changes. Experiments and user feedback show it produces better visuals, smoother motion, and a lot more versatility for tasks like camera panning, local motion editing, and motion transfer. That's the main takeaway: a unified, efficient way to guide movement in generative video. And there you have it. A deep dive into how this method brings order to the chaos of video generation. Whether you're animating a single object, simulating a camera move, or transferring motion from one scene to another, this approach makes it all feel intuitive and precise. Thanks for diving into this fascinating research with me. See you tomorrow.